So today I'll be talking about TrueAllele for Africa. What is informative genotyping? That's really what I'll be talking about, and I'm not going to... Most DNA that's analyzed is not terribly informative. The usual result we see in the States is inconclusive or uninterpretable DNA mixtures. And what is cybergenetics TrueAllele computer analysis? The key idea is that you use probability as a way to preserve identification information. And I invented this over 25 years ago. It's best described non-mathematically as an example. This is from a case. You have a handgun. There's a question of who was shooting. And what TrueAllele does, you have a 4-person mixture. It unmixes the mixture. Why do you want to do that? Because then you've reduced it to 4 single contributors, and dealing conceptually and with a legal system explaining it with one contributor is a lot easier than dealing with a mixture. So the computer unmixes it for you so that it's now a much simpler problem. So all the genotypes you'll be seeing today are unmixed. The result that happened in this case is that one person was excluded, another person pled guilty, and no trial was even needed. These are the goals some of the goals of Cybergenetics collaboration with UCT to show sexual violence does exist as a problem in Africa. I think that's been addressed already the last few days. To demonstrate that uninformative DNA can be informative, to reveal the presence of multiple contributors, and to find serial offenders by comparing DNA evidence between crimes. So I'm going to give you some brief examples, not all the case context. Each of these stories have been our lectures and other forums, just a few slides. There's a serial rapist in California 10 years ago who's attacking single women and their children, and he goes from crime scene to crime scene, breaking into their homes. Across the different scenes, we have over 36 items of evidence. And the bottom line is they're all 3 to 4 person mixtures, and the crime lab can't interpret anything. It's using CPI, which is useless for these types of mixtures. It has nothing to say. There's a grand jury coming up. The person's about to be charged. Cybergenetics gets a call. We have to produce results, which we do quickly for this case. And summing it all up, this is a match table. And what you're seeing on the left are 9 items. They actually represent genotypes from them. And they're in groups, 3 different groups. Each is from a different crime scene. So you're seeing the first set of 3 is from one crime scene, the next is a different apartment, and then the last 2 are from another apartment. Across the top, we're seeing 6 references that are again grouped into columns of 2 items. That's the first crime scene, the second crime scene, the third crime scene. If you look down the diagonal, you're seeing that within each crime scene, TrueAllele has analyzed these uninterpretable mixtures, these 8 items, compared it with the 5 items and the 1 suspect, and we're showing the likelihood ratios, the DNA match statistics, using logarithms, which is the number of zeros. So 6, 1 followed by 6 zeros is a million. It's easier to look at a number like 18, which tells you it's a billion, and then to write it out. And you see how TrueAllele has separated things out. Some of the rows have 3 match statistics, meaning that the mixture was separated and the amount of association with each of the 3 components is revealed on this table. The last column is Billy Ray Johnson, who was the perpetrator, and you see match statistics 6s are in the millions and so on. And in the end, he was convicted largely on the basis of the DNA evidence. So how do these other methods lose information? There's a funnel of loss. Labs can choose to not use an evidence item, like it's a hat. We don't do hats. They may choose to not generate DNA data. They often don't even infer a genotype. When they get a genotype, they may decide it has too little information to go to a database or to report. And the result is most evidence is never never appears. And here is those same processes, those 5 steps I showed in the last slide, in the left column about evidence items, data, and so on. And most evidence isn't reported because there's so many points at which people sort of know in the lab they're never going to be able to interpret it anyway, so why bother? And it's the lack of the ability to interpret that's driving saying, oh, it's a hat. I'm looking at the column second from the right. It's a hat. It's going to have 5 contributors. Let's not look at it. There's not enough DNA in it. The peak heights aren't tall enough. There's too much variation in the data with stochastic thresholds. Oh, there's more than 3 or 4 contributors. Let's not look at it. Or in the end, you get all the way to the end and the lab says, there's a reporting threshold. It's only 100,000. We're not reporting it. So information is lost at every step. What TrueAllele does, and it was designed this way, is it preserves DNA information. It separates, and what I'm showing in the column now under the method is how does it overcome every step? It's a mathematical problem that's being solved. Any mixture will have hundreds of variables, and TrueAllele, based on the data, will solve for the unknown variables up to probability. And of all those variables, the only one we really care about are the genotypes. The genotype for each contributor at every locus, because that's what we can compare. It solves for the stutter and the variation, does all that. But those are nuisance variables. So in the end, it produces likelihood ratios, and there's a list. I'm not going to read through it. There's little time. But using a full Bayesian model, it models all the variation and fills in all of the hidden variables to solve the problem. Here's an example, which I spoke about in a different way yesterday. Yesterday, we showed a demonstration at the workshop of how you could have a mass disaster and using kinship and a TrueAllele database that preserves the information as these genotypes with probabilities. It's now a student exercise that we use because it only takes maybe 10 minutes to do the entire problem with everything. We showed that yesterday in the workshop. So I'll describe the steps. There was a bus crash in Komatipoort, South Africa in 2008. There were burned victim remains. Relatives submitted their DNA to help identify the remains, but it was at most one relative for each remain, and the data was sent to Cybergenetics to take a look. So here's a list of the victim remains that you're seeing on the left. This is just ordinary FSA files that we received at the time. Might have been, I don't think they were HIDs, I think they were FSA. And so in TrueAllele, you basically just do the computer does a quality check on the data, gets uploaded to a database, and then the computer automatically solves for the genotypes. And it's all automated. So there's now a database, and there's a remains column with genotypes that are in there for a few minutes of human work. Next, there were relatives. And here, what TrueAllele needs is there were text files of 16 relatives. You're seeing that in the sample column. That gets uploaded, just upload them to the database, along with a description of what's the relation of each of these profiles to the missing person. That's the column on the right. So there's a file that essentially has a few columns, 16 rows, that gets uploaded. That takes, 15 seconds. Now the computer is going to infer up to probability using genetics and mathematics, what is the probability genotype of that missing person. If you have full information from pedigrees, we can recover a complete genotype from people's relatives. If you have, for example, a mother and a child, you could recover an alleged father and use it in paternity. In this case, we have one relative, and up to what that information can tell us, we can work out the probability of these of what would the grandson look like of that person. And so now we have evidence with probability, we have the remains. And so in the database, we have, these are the family reconstructed genotypes up to probability. We have the remains. The database automatically matches them. And then we end up with these match results. The rows are the different victim remains. The columns are the relations of those missing people. And the match statistics are, again, log values. They're typically around 2 or 3, which is about 100 or 1,000. And that's used to associate the victim remains with the families. Visually, if you look, these are the links that are found in the database along with those likelihood ratios. So the concept in TrueAllele is that the system will infer genotypes up to probability from samples, degraded DNA, mixtures, kinship problems, whatever they are, and then whether it's on your computer or you're making comparisons to look at the likelihood ratios, or it's happening on a database, either in your lab or on the cloud, likelihood ratios are calculated. The advantage of a database is you can go between multiple scenes and multiple labs and do things in a more global way. So I've heard a lot about probabilistic genotyping over the last 2 days. You might think that's strange. I didn't come up with the term. Somebody else did. And it's kind of stupid, honestly. I was going to say silly, but it's just stupid. Everything in science is probabilistic. Do you ever read like a journal article, you open it up and there's a confidence interval? Oh my God, they don't know that the number is exactly 5.2. Of course not. Everything's a probability distribution, if there's any uncertainty at all. And a genotype is actually a statistical variable that is a summary, a stand-in for the data. You can't compare data directly with data, but you can compare these statistics called genotypes in a likelihood ratio formula. And any statistical variable has uncertainty. You might think an exact profile doesn't, but that's not what I'm talking about. And the only way to represent uncertainty in science is with probability. So everything is a probabilistic genotype, even the lame CPI method. Some people may still use it, but the one that loses all that information, it mathematically is a Bayesian constructed probability. It just doesn't have much information in it because it loses all the peak height information and the pattern just throws everything out with thresholds. The difference is that you've got very primitive probabilities, the very sophisticated probabilities. TrueAllele, again, has hundreds of variables and takes hours to solve, and it solves for everything, is how much information does it get? And the point is, you can have lots of probability distributions, but some are more accurate than others. So think about that, because that's what I'm going to get to. This is a science talk. I want to show you some new results, right? I don't want to tell you, I've been at TrueAllele for 25 years. That's boring. Let's look at something new. Okay, so this is only 10 years old. I have a nice paper on this. Other people have looked at these likelihood ratio distributions. They're incredibly powerful. We calculate them in TrueAllele. We have a method where you can calculate. Let's look at the one on the left. What's a non-contributor distribution? The left axis is log LR, that is the powers of 10 of an exclusionary match statistic. Imagine you took everyone in the world and you compared it with your genotype. You would get that distribution on the left. That's the distribution of largely negative log LRs, exclusionary match statistics. That shape tells you so much about it. You can see that the center is around -6. It's pretty informative. That's the range in which, if you have an actual match, because nothing's matched yet, this is all a property of that statistical genotype. We've not made any comparison. It's just an inherent property of the genotype. You can use it for validation studies by looking at 50 or 100 genotypes that all have uncertainty and looking at them together. And then in 1 minute, you've done, well, in the old days, 15 years ago, it would take us months of computation. You just instantly get this from a set of genotypes. Very powerful stuff. The one on the right is the contributor genotype, which is based on the probabilities that you find from the evidence. Basically, from these evidence genotypes, what would be the distribution of genotypes that describes what is going to happen when I make a comparison with either the wrong people or the right people. If I make a comparison with the right person, they'll pretty much fall within that bell curve. If it's the wrong person, they'll be far outside of it. So here, there's no comparison. This is just the genotype. Suppose I do make a comparison. This comes from a bank robbery case in New Orleans, Louisiana. The match statistic was 200. That log value is showing it in green. You see an arrow at around 2, because it's about 100. And what you see is that arrow is within the distribution on the right, the contributor distribution. It's not really in the non-contributor distribution on the left. But if you look at that very tiny tail probability to the right of the green arrow that keeps going, then you can get an error rate. So these are ways of describing genotypes and how they behave. In the Uber ride over, somebody was actually listening to a lecture on Wittgenstein, one of my favorite philosophers. And I won't go into it, but the key idea, which they said on the podcast, was you define things by how they're used. That was Wittgenstein's brilliant thing about language. How is a genotype used? You're going to compare this with another uncertain genotype in TrueAllele or with a definite profile, and this shows what the space of all those comparisons is going to be along with the probabilities. Now, the new thing of something that we have in a paper coming out soon is you can use the same approach to measure the accuracy of genotypes. See, it's one thing, before I was talking about genotypes, how much information, average statistics, error rates, fine. Different question. Suppose I have a genotype that's been calculated from evidence, and I want to know how accurate is it as a classifier. That is, when I look at the likelihood ratio, is it going to tell me that somebody's a contributor or not a contributor, to the right or to the left? How accurate is it going to be? Is it going to be getting it right 99% of the time, 99.9% of the time? Is it going to be getting it wrong 10% of the time, in which case it's total rubbish? Because why would you convict somebody or execute them or set them free if your answer is wrong 10% of the time? You may as well go back to eyewitness identification. Okay, so the further apart, intuitively, the further apart these curves are, the better the discrimination is. And the closer they are, the worse it is, because they're not discriminating anything. And if they overlap completely, it's basically garbage. Okay, so in this case, for the bank robbery, the discrimination accuracy was 99.97%, which is good for classifier. AI is typically around 90%. Okay. This is a case that has been written up so much, and so much nonsense has been written about it, it's incredible. Imagine you do science, you go to court, you present it, and there's two different results, and then somebody who is an expert for the other side, who's a psychologist, academic, lawyer, keeps writing articles that are very long, proposing all kinds of weird stuff. Maybe it happened this way, maybe nothing that they would ever test because they're not scientists. So everything is with these words going back and forth. And so I thought about this. I was like, why bother with words? We're scientists. Why not just measure the accuracy of the method? So what's the problem? There was this case where somebody was accused of having baggies of methamphetamine under his arms. The question is, was the evidence really there? Wasn't it there? And two different methods were used. The lab originally used star mix, which is like Euro 4 mix on this side of the Atlantic. And what they found was a match statistic of like, I don't know, 1 in 25, a very weak exclusion. Actually, I don't think it was even that high. It's like -1 was the log. And then we were asked by the defense, again, to analyze, and we said, no, it's more like 1 in a million. The guy's not there. And anyway, the prosecutor argued, the judge said, I want to hear it. So things moved on. But we're able to take the genotypes and measure their accuracy. The TrueAllele curve on top, you see that the non-contributor and the contributor are widely separated. And when we measure the accuracy in this forthcoming paper, the accuracy was 100%, up to a few decimal places. It's perfect separation. But now, in terms of discriminating non-contributors from contributors to classify them, on this low-level case with the thresholds that you're about to see, the discrimination was over only 90%. That is, the curves are overlapping. And if you look at that poor green match statistic that's right near zero, it's in both curves. It can't be separated. So this is what thresholds do to methods that use thresholds, which as far as I know is everything but TrueAllele. So the first row is TrueAllele. The first column says there's no cutoff, there's no threshold, there's 21 loci, 210 peaks, the separation is large, and the exclusionary statistic is -6, 1 over a million. The lab using StarMix used a threshold of 40, and you see they only looked at 24 peaks. How can you be looking at a mixture of like 2 or 3 people, 24 peaks? I have no idea. But anyway, the result is their numbers around -1. But that's not all. We did a sensitivity study, and we changed the threshold. Well, surely you would get the same answer every time, right? No method would be sensitive to the threshold, right? A lab sets its threshold. You use it forever. You rely on it, except that with low-level mixtures, if you change the threshold, we see with other software over and over and over again, you change by 6 orders of magnitude what the likelihood ratio is, often changing an inclusion to an exclusion. You can read about this in the forthcoming paper. Okay, TrueAllele is reliable, over 40 validation studies, 8 published, over 50 admissibility rulings, over 500 client agencies, prosecution, defense, the FBI, investigators. When you don't get information, people send their data to Cybergenetics. Even from Africa, it's happened. Okay, and studies have shown that it's sensitive, specific, accurate, it's informative, and it's fun and easy to use. DNA for Africa. This is my last real slide. DNA information solves crime. And why do you care about information? Isn't forensics just a matter of following protocols? You grind things up, you put them through, you put them into software, and then you don't report most of the time? Isn't that the point? No. The point is to preserve information so the information can be used for crime, preventing crime, solving and promoting justice. And the trick, or the idea scientifically, is to use information preserving genotypes, not probabilistic genotypes. You have that with CPI already, and you want to move on. You just want to use information preserving genotypes. Then you can connect crime and criminals and have more effective DNA databases. Computer automation, which is TrueAllele offers, does this for you. It only does 2 things. It infers genotypes accurately, and it gives you accurate match statistics. That's the easy part. The important part for Africa is that it scales up. The Kamataport bus crash, as there were witnesses yesterday, right, took Bill Allen in our office maybe 10 minutes in the videos of showing what he was doing to solve the whole thing. People would take a lot more time and get a lot less information. You want something that scales for Africa. You're not going to find and pay for thousands of people to look at data and throw out all the information and not find anything. What's the point? You're better off having computers automatically getting you the right answer so that you can get justice, which would be a very good thing. I'll stop there. Thank you.